Hello, welcome to the CSE 351 Introduction to Data Science. This is the fourth video lecture from the Introduction to Data Science series from the topic of linear algebra. Today's subtopic is matrices. In the first three videos we discussed vectors and the property of the vectors, and also some concepts and definition and examples. Today the focus is on matrices. First, why matrices are so important in data science. Basically matrices are the most frequently used data containers for the data science problems. The reason is as follows. Usually we are dealing with high dimensional data, and also in different problems we are given some samples. So we have samples, and each sample is a vector of nth dimension. So if you want to have a collection of data, this collection of data would be a two-dimensional array whose usually rows represent the samples and the columns represent features or attributes collected for that sample. So when we are dealing with any type of data science problem, the input usually is an unstructured and usually not clean data sets, and then your task is to clean these data sets in order to provide a matrix, which we usually use an Excel file, and then we are going to do some operations, some manipulations, and then also we may apply this matrix to an algorithm in order to do some prediction or get some insight or intuition about the data. And also another reason we are using matrices in data science, usually matrices are used for transformation. For instance, if you have an image and you want to rotate that image, it simply can be done by multiplying a matrix to that image. So all sort of transformation on a vector, if you want to have a vector, you want to change the dimension, you want to increase the amplitude, can be done using a matrix transformation. Another reason is if we already talked about the importance of vectorization for implementation. Also, when we are dealing with matrices, its implementation is very fast and easy. Matrices also provide a very efficient way to have a compact form for mathematical formula, which are frequently used in data science. And also matrices are a way to show the span of a vector space, where we can put all these vectors and stack them and represent them as a matrix. There are much more reasons that we are using matrices in data science, but for the sake of being brief, I just mention a few of them. Matrices, how to present matrices. Usually we can have two different views of matrices. The first one is a matrix. It could be viewed as a two-dimensional array. For those of you who have done programming, so you're dealing with multi-dimensional arrays, a matrix is a two-dimensional array. However, the elements in each subdimension should be equal. Otherwise, an array of arrays not necessarily show a matrix. So in this case, we can say, let's say X is an array of arrays. Say this is 1, 2, 3, 0, 5, 2. This is a matrix. This is a two-dimensional array. The standard form we are using to represent a matrix is using a rectangular bracket or using large parentheses. So for instance, if I wanted to show this matrix in standard form, I use a large rectangular bracket, but I put 1, 2, and 3, 0, and 5, and 2. Or I can use also a large parentheses, put 1 and 2 and 3, and 0, 5, 2. There is no need for putting comma between each elements. Another way of looking at a matrix is a matrix could be viewed as vector containers. So we have a set of equal size vectors, and then if we stack them horizontally or vertically, then we can form a matrix. I like this view of looking at matrices better than the other one, because that gives you more insight about the operations later on we are going to apply on matrices. So in this case, because we wanted to distinguish between a vector and a matrix, from now on I will stick to this rule and show a vector as a lowercase letter with a arrow on the top. So that arrow shows this is a vector. Note that also a vector could be viewed as a matrix, a one-dimensional matrix. So this is important from programming point of view, especially in NumPy. You distinguish in your program you're using a one-dimensional array or a two-dimensional array, because NumPy treats these two way of presenting vectors differently, and if you are not consistent, your program may throw an error. So in this case, if we have vectors like x of dimension of 1 times n, that means this is a vector of dimension of n. This is a row vector, so whose elements are x1, x2, x3, all the way xn. And also if you have, let's call this one x1 with a superscript, so these are 1, 1, 1, and then we have another vector, let's call this vector x with the superscript 2, and then this arrow on the top shows that this is a matrix, and then this one should be also the same dimension. This is a row vector x1, x2, all the way to xn, and with the superscript showing this is the second vector, and then all the way down to the last vector, let's call it with the same dimension. Let's call this vector m. So this vector's elements are as follows: x1, x2, xn. This is mth vector. So these vectors, all of them that have the same dimension, can be expressed as a matrix. So I can put them like this: x1, x2, and then all the way down xm. So this is another way of representing a matrix. The dimension of this matrix is m by n. So in many applications, it's better to look at a matrix in this way. So a matrix is a stack of vectors, either they stack horizontally or vertically. Note that all of these vectors belonging to this matrix, they should have the same dimension. Otherwise, you cannot stack a vector of dimension 2 on top of a vector of dimension of 3. So these are two ways of showing a matrix. And also this could be expanded to all elements of this matrix, x11, go all the way to x1n, then x2, 1, going all the way x2n, and if you continue all the rows, you get xm1, going to the way xmn. Sorry, and n. Okay, so dimension and the type of elements of a matrix. This is very similar to what we use for vectors. If you recall, in order to have to show what is the dimension of a vector and also what are the type of elements in a vector, then we use a notation, a mathematical notation. X belongs to the domains from which the elements of this vector are sampled. If, for instance, these elements are real, we put R, and then we show the dimension by a superscript. For a matrix, we are using capital letters. So the notation is we use capital letters to show a matrix. Okay, so and also if I wanted to show the dimension of matrix, then I can say, let's say A is a matrix belongs to, if the elements of this matrix are real numbers, then I can put R, and then if this matrix has n row and m column, I put n times m here as a superscript. Another way of showing this, we can say A is a matrix of dimension n times m. That matrix belongs to R n times m. So they both are equivalent. This is more details. If we are already sure about the type of elements in a matrix, then we can simply show this short way of denoting a matrix, n times m. Note that we also can have a vector as a matrix. So I can say x, if I say, for instance, B is an n by 1 matrix from, let's say, integer numbers, that means B is a vector. So B is a vector. So what is the dimension of this vector is n by 1, or we can say this is a one-dimensional array of n elements. They are both equal. So then we can say, show the B as a vector belonging to Z n. That's the same. So don't confuse that a vector could be also a matrix of dimension 1. And also a vector could be one-dimensional, not two-dimensional. In here, this definition is a two-dimensional representation of a vector, whereas a vector has one dimension. So when you work with NumPy and then do the vector matrix manipulations, you will better grasp the difference between one-dimensional and two-dimensional representation of a vector. Okay, so we use capital letters in order to denote a matrix for throughout this video. Sub matrix and indexing, like vectors, we can also slice or extract a sub block of a matrix. The notation we are using for a matrix, let's say A is a matrix of dimension n times m, which belongs to a domain, which this domain could be anything. I don't want to just limit ourselves to real numbers. Could be any domain of different types of number, rational numbers, integer numbers, or real numbers. So the dimension is n times m. If I want to extract one element, let's say I wanted to extract the elements in ith row and jth column, then A, I, and J. So that's in order to extract the element in row I and column J. That's the notation we are using. If you wanted to extract a row of a matrix, the notation we are using is like this. Let's say I wanted to extract the third row of a matrix. Let's say this matrix is a matrix n by m. Then if I wanted to extract the third row, then the notation I use is I, 3, and I use a colon here. That means this is the third row and all columns. This is very consistent the way that NumPy will treat a matrix and also slicing a vector or matrix. If you wanted to do practice, I have uploaded the slides where you can see how we can build a vector or a matrix in NumPy and how we can do all these manipulations. So this one is equal to a vector, which for vector I use a lowercase, and I put an arrow in here to show this is a vector, and it is from the third row, and then that's the vector. And then the dimension of this vector is the number of this vector belongs to domain D, and because this is a row vector, the dimension of this vector is m. Right? If you wanted to extract a column, let's say if you have the matrix A of dimension n times m, and I wanted to extract, let's say, the fourth column, then I used this notation A all the rows, but go to the fourth column. And then I can show you this one as a vector, all rows, and then fourth column, sorry. Sorry. And this is also belongs to the n, because this is a column vector. So this is the way we are showing a row or column of a matrix. And a row and column of a matrix is a vector and dimension. If this you extract a row vector, the dimension is equal to number of columns, and if you extract a column vector, the dimension is equal to number of rows. So that's the way we are indexing a matrix and also a sub matrix. Next, we are dealing with lots of special matrices throughout this course. For each of them we use a special notation. We start by identity matrix. An identity matrix is a matrix that all of elements are equal to 0 except the elements on the main diagonal, and all of these elements are equal to 1. So so we can have the definition for a matrix. We usually use the capital letter I in order to show this is an identity matrix. And this matrix, let's say, has m row and n column. This is a matrix that whose elements are I, I and j. So these are the elements, such that these elements are equal to, so ij is equal to 1 if I equals to j, and ij equal to 0 otherwise. That's an identity matrix. So let's say if I have an identity matrix of dimension m by n, we note that an identity matrix is a square matrix. A matrix is a square when the number of row and columns are equal. So in this case, m is equal to n. So this is a square matrix. So if we define a matrix of dimension m times n, and if m equals to n, then A is a square matrix. Okay, so therefore we can write this one as an m by m. And then if m, for instance, is m equal to 3, then I is equal to matrix. All elements are 0 except the elements on the main diagonal. That means this element is 1, other elements are 0, 0, this element is 1, this element is 0, 0, 0, and 1. As you see, all elements on the main diagonal are 1. Okay, very, very simple and straightforward, no magic. The Second type of matrices we are studying is matrices whose elements are all zero. So we call this matrix as a big zero m times n. That means this is a matrix that contains all of elements are zero. So this is the matrix, or m times n. It's a matrix of whose elements are O, I, and j, such that O, I, and j's are zero for all I and j. Okay. The next types of matrices are sparse matrices. So sparse matrices are matrices that the number of non-zero elements in these matrices are much smaller than number of elements in that matrix. So if I have a matrix S whose dimension is m by n, and then number of elements in this matrix, so number of elements in this matrix is m times n. So, and then we call also nz of S as the number of non-zeros elements. Therefore, this ratio, we call it R, which is equal to nz of S divided by m times n, should be much, much, much smaller than 1. That's a definition for sparse matrices. This is very important topic, and these matrices are used a lot, especially when you wanted to do matrix factorizations, and also in linear regression models when the predictors are sparse, then there might be a much simpler way of presenting the data, and also we can better compress the data if matrices are sparse. Symmetric matrices are matrices that the elements I and j equal to j and I. So let's say S is a matrix of dimension m by m. So symmetric matrices are square matrices. Their symmetric matrices are square matrices. Then let's say if the element of this matrix are S, I, and j, then we know that Sij should be equal to Sji. So that's the Sji. So an example, let's say S is equal to 1, 2, 3, then this element should be 2, this element should be 3, this is 5, and then if this is 6, this element should be 6, this element, let's say this is 10, this is a symmetric matrix. So if you wanted to see if a matrix is symmetric, then if you consider the main diagonal, all elements in here should be elements that mirror each other should be equal. So 2 equals to 2, 3 equals to 3, and 6 equals to 6. Symmetric matrices they have very nice properties. They're used a lot in multidimensional probabilities, in particular in multidimensional Gaussian probabilities, and also we use them when we wanted to do dimensionality reduction. We have a matrix, then we make a symmetric matrix out of that matrix, which we call it a correlation matrix, and then we can compute some eigenvectors, and then we can do some sort of dimensionality reduction called PCA. We will get to this in future videos. Another types of matrices are positive definite matrices. So a matrix is called positive definite. Let's say we have a matrix called M. Let's stay with the black color. Let's say M is a n by n, say, symmetric matrix. Then these matrix is positive definite. This is a matrix if and only if X transpose M times X is always positive for all X's belongs to Rn. So an X is not 0. So that's a positive definite matrix. So I don't want to go through the details, but these matrices are used a lot in linear algebra, and also we will show that Gaussian probability, what we have in exponent of the Gaussian probability, is a positive definite matrix. And these matrices they have nice properties. Note that in here X is a vector, and then X is a column vector. Then we take the transpose, that will be a row vector. So if you wanted to see the dimension, the dimensions are as follows. So n is an n times n matrix. X is an n by 1 vector, and the transpose would be also 1 by n. So the results of this matrix vector multiplication is a scalar, right? That would be a scalar. And this is also another way of we are showing the distance criteria or distance matrices, where the x is a vector and m is a covariance matrix. But as I said, I don't want to go through details. Just have in mind what is a positive definite matrix. Diagonal matrices are, as I said, the matrices that these are the matrices that all elements on diagonal of that matrix are non-zero, and then all other elements are zero. So if the let me just use the black color. If D is an n by n square matrix, then whose elements are d, I, and j, and these elements are d, I, j is not 0 if I equals to j, and d, I, j is 0 when I is not equal to j. So this diagonal matrix is very similar to an identity matrix. Basically, an identity matrix is a subcategory of diagonal matrices. So for instance, for a, like say, a 3 by 3 matrix, so have, let's say, 5 0 0 0 2 0 0 0 10. So that's a diagonal matrix. So as you see, only elements on main diagonal are non-zero, and all other elements they are zeros. So these elements are all 0, and also these elements are also all 0. So these are diagonal matrices are the matrices that we like them in linear algebra and also in data science, because they make the calculation much easier, less complex. Okay, in here I'm going to talk about some popular functions or operation on matrices. The first operation is transpose. So in order to, let me add the page in here. So the first property I wanted to talk is transpose of a matrix. So if you have a matrix, let's call it A of dimension m by n, and then we denote the transpose of this matrix by A T. We use a superscript capital T, or sometimes we use A prime to denote the transpose, and then dimension of the transpose of a matrix is n by m, n by m, and the transpose is obtained by basically swapping the row and column of the original matrix. So Let's clarify this by a simple example. Let's say we have a 2 by 3 matrix which has 2 rows, 3, 7, 0, and the second row is 1, 10, and 5. Then A transpose, which is 3 times 2. Also sometimes we use prime, which is 3 times 2 is basically by swapping the row and column. So basically I get the first row of this matrix and I put it as the first column of this matrix. So this one common becomes the first column of this matrix. 3, 7, and 0. And then I get the second row and put it as the second column of this matrix. So here it would be 1, 10, and 5. That's how we obtain the transpose of a matrix, by swapping the column with rows, or if you have consider each row as a vector, we just put the transpose of that vector in the transposed matrix. So the transpose of a matrix and transpose operation has a couple of properties. These properties are, if you have a matrix A, if you take the transpose of that matrix and then transpose the transposed matrix, then you will get the original matrix. I just dropped the dimension for the sake of simplicity. And also, if you add up two matrices and then take the transpose, this is equivalent to taking the transpose of individual matrices and then sum each transpose individual matrix. And also, if you multiply two matrices and then take the transpose of both, then this is equivalent to take the transpose of the individual, but you need to reverse the order of multiplication. That would be equal to B transpose times A transpose. Times A transpose. So note that in many cases we are multiplying two matrices and we wanted to transpose the resulting multiplication. We cannot just simply move the transpose to individual. It's possible when you swap these two transpose matrices. It's very straightforward. Why? Because if you consider the dimension, then if you just multiply this transpose, the dimension doesn't match up, and then you will have an error. And also, if you multiply, if C is a scalar, then if you multiply C by A and take the transpose, this is equal C times A transpose. These are some properties of transpose of a matrix, and also if you inverse a matrix, we will talk about inverse shortly, and then you wanted to take the transpose, this is equivalent to taking the inverse of that matrix and then transpose it. So that's also another property. Sorry, I forgot to this. We can first transpose and then take the inverse. This is the transpose operation or transpose of a matrix. All you need to know. Second is a norm of a matrix. So what is norm of a matrix? So the norm of the matrix is very similar to norm of a vector. We need to square individual elements, sum them up, and then take the square of all elements. So basically, if I define A as an m by n matrix whose elements are I and j, I need to square all elements and then sum them up. So basically, the norm of a, this is also norm 2, is the square root of a11 squared plus a12 squared plus a21 squared plus go all the way a22 to n plus all elements squared a m n squared. So the number of these elements are m times n. M times n. We squared all elements, sum them up, and then take the root. This is the norm of a matrix. So later on we relate this one to norm of a vector, and how we show that how using a matrix multiplication with a vector we can obtain these norm rather than doing some loops. We can do the vectorize operation and find the norm of a matrix. Next operation is the trace of a matrix. So next I'm going to talk about the trace of a matrix. So let's here add a page. I wanted to put each of these special operations on one page. So use green for the patient. The trace of a matrix. So what is the trace of a matrix? So basically the trace of a matrix, if you have a matrix of dimension n times m, then the trace of that matrix is sum of the elements on the main diagonal. Sum of the element on the main diagonal. So we denote the trace by tr. The trace of A is equal to sum of the elements on the main diagonal. So the trace equal to A I. So it's very simple. So you just and also we note that the trace is defined for square matrices. So that means and m is equal to m. A is a square matrix. So, for instance, if A equal to 5 minus 9, 0, 3, 1, 5, 2, 1, 100, then the trace of A is equal to 5 plus 1 plus 100. This is equal to 106. Note that the trace of a matrix is a scalar. That's important. So when you apply the trace, the output is a scalar. So note the trace of a matrix is a scalar. In other words, the trace is a function that maps the R n times n to R. That's how. The trace of a matrix has some properties. So it's very simple to verify that the trace of A is equal to the trace of A transpose. If you transpose a matrix and take the trace of a matrix and its transpose are they're equal. Another property is if you multiply two matrices and take the trace, you can, if you swap to the multiplication, then the trace are also preserved. That means that if you have the trace of A times B, this is equal to the trace of B times A. And also if you have the sum of two, the trace of sum of two matrices equals to the trace of the individual sum of the trace of the individual matrices. There are some other properties, but I think that's enough for this topic. The next is inverse of a matrix. So what is the inverse of a matrix? So next topic is inverse. We'll add a page in here. Sorry, add a page here for inverse. We have the inverse of a matrix. So we note that the inverse is defined for square matrix. So if A is an n by n matrix, that means A is a square matrix, then the inverse of A, the inverse of A denoted by A inverse, such that A times A inverse is equal to identity matrix. And we know that this is the definition for identity matrix. It's very similar to inverse of a real number, but in this case, instead of getting a scalar, we get a matrix, an identity matrix. So there are some properties associated with the inverse of a matrix. So if A is an n by n matrix, then if you multiply A by B, so let's say also and B is an n by n matrix, then if you multiply these two matrices and take the inverse, this is equal to taking the inverse of B and then multiplying by inverse of A. And also, if you transpose a matrix and take the inverse, this is equivalent to taking the inverse and then transpose the matrix. And also, if you have sum of two matrices, then we can apply. If you have A plus B inverse, you can inverse the first matrix and then sum result to B minus B inverse. So these are some property of inverse. So here we don't discuss how to compute the inverse of a matrix. There are a number of algorithms to efficiently compute the inverse of a matrix. This is also in data science. Sometimes we avoid taking the inverse because we are dealing with matrices of dimension of millions, and if you wanted to take the inverse, that's sometimes computationally expensive. There are, however, some method device in order to reduce the computational complexity, but we in general want to avoid taking inverse. And sometimes if the matrix is high dimensional, the inverse might not be very stable. So that's all about the inverse of the matrix. And then the last type of operation is taking the determinant of a matrix. So if you wanted to take what is the determinant of a matrix, so next is the determinant the determinant of a matrix is denoted by that of A, or sometimes they use two bars, then put A inside. These are all two notations we use for determinant. So determinant of a matrix returns a scalar. So if you have determinant of A as a function, it will map an n by n dimension to R. Also, we note that determinant is only defined for square matrices. That means the number of rows should be equal to number of columns. There are a number of ways to calculate the determinant of a matrix. So for simple case, if you have if A is a 2 by 2 matrix whose elements are A, B, C, and D, then the determinant of A is equal to A times D minus B times C. But If you wanted to have a generalized closed form formula for determinant, if we assume that A is an n by n matrix, then the determinant of A is equal to the multiplication of its eigenvalue, where lambda I is the ith eigenvalue of A. We will talk later about how to calculate the eigenvalue of a matrix when we will talk about the dimensionality reduction, but for us, how to calculate the determinant of a matrix is not important in this course because there are lots of mature and well-defined libraries by which we can just define the determinant of a matrix. What is important in here to have an intuition about the determinant of a matrix. So what exactly we are doing when we are computing the determinant of a matrix. So basically, determinant of a matrix, intuitively, the determinant of a matrix is, so that is a volume of n dimensional parallel piped. I will explain what is parallel pipe. Parallel piped formed by columns column of A. So what does this statement mean? That means if we consider the columns of matrix A as side of a parallel piped, so parallel piped is a geometrical shape, then the volume of this parallel pipe is the determinant of a matrix. So let me just give you a simple example. I hope that will simplify the understanding of determinant. We will consider a very simple case. We will consider a matrix of a two-dimensional matrix. Let's say A is 3 by 0 and 0 by 4, right? So in here A consists of two vectors. So let's say vector A1 and vector A2. Okay, so if I use the Cartesian plane to show these two vectors, then I have this Cartesian plane. So A1 basically is, so you know that A1 is 3 and 0, and A2, two vectors are 0 and 4, right? So A1 here is this vector, three units, and is 4. So this is A2 and this is A1. Okay, so what is the, in here this is a two-dimensional space, and what is the volume is basically a surface, because volume form for 3D, but we have a two-dimensional space, therefore a volume is converted to a surface. So what is the volume of these two vectors? So volume is simply is this rectangle. This is the volume, right? So what is this surface? So it's basically the surface is equal to A1 times A2, right? So this is the surface or the volume defined by these two vectors. So how we compute the determinant of this matrix? We know that determinant of A is equal to determinant of 3, 0, 0, 4. So it's basically equal to 3 times 4 minus 0 times 0, which is 12, which is the surface of this parallel piped figure. So now what is important in here, when the determinant becomes 0, if the vectors of a matrix, they are in the same direction, then the determinant is 0. So we usually don't want to have a matrix whose determinant is 0, because that causes a lots of problem, because when we compute the determinant, when we wanted to compute the inverse of a matrix, we basically compute the determinant of that matrix first. If you were working with the multidimensional probability, for instance Gaussian probability, we need to compute the determinant of covariance matrix. If the determinant of covariance matrix is 0, then that probability is not defined. So for this case, for this example, if we have two vectors, let's say I use different colors. Let's say if we have vector A3 and we have another vector, let's say let's have A2. These two vectors are, what is the area surrounded by these two vectors is 0. That means the determinant of this matrix is 0, because these two matrices are in the same direction. So that sometimes is ill condition in matrices, and then we want to avoid that. That means one of these two vectors is redundant, because we have all information in that direction from A3 for this example. A2 is only a scale version of A3. So that's a conceptual and a definition and understanding of determinant. Okay, here we are going to talk about linear combinations of vectors and also linear independence. We wanted to present a matrix notation for linear combination of vectors. So consider vector v1, which belongs to Rn, or we can also use the matrix notation. So let's say v1 is n by 1, one column and n rows matrix. So also we have another vector v2 whose dimension is also n by 1. Then we define v3, which is a vector, by multiplying vector 1 by a scalar, we call it c1, and then sum it up with v2, but before that we also scaled v2. So in here v3 is a linear combination of v1 and v2. So that means if I have v1 and v2, and also if I have the c1 and c2, then I can generate v3. In other words, if I'm in a space that we have v1 and v2 and v3, I don't need to have v3. By having v1 and v2, I have all info, and also c1 and c2, I have all info to form vector 3. So that means in here v3 is linearly dependent on v1 and v2. But in general case, let's say we have k vectors. So let's assume we have k vectors, vector v1 all the way to vk. Then these vectors, we call them linearly independent if we cannot express each of these vectors in terms of the others. Then these vectors are all linearly independent. In other words, so we call these vectors linearly independent. So let me add another page in here. Call them linearly independent if we have a linear combination of them equal to 0. Let's say cv1 plus c2v2 plus cnvn equal to 0. Then c1 equals c2 equals to cn, all equals 0. So that means there is no way we can express these vectors in terms of each other, any vectors in terms of any combination of others. So these set of vectors which are linearly independent, they are extremely important in field of data science. So in order to have a practical example, let's say we wanted to see if we can predict the grade of a student of a class from different factors. Let's say student height, student health, if the students go to gym. So you can consider these factors as these vectors, right? So if we would like to find some factors, or what we call it in terms of a data science parameter as a features, when they are linearly independent. Otherwise, if we have two features, they are dependent that means they don't give us enough information, because one is, if I have one, I can also have the another one by scale it and sum it with another vectors. So ideally, when we wanted to do prediction, we would like to have features that are as independent as possible. Otherwise, our problem has some features or vectors which are redundant. So we can express this relationship in form of matrices, a matrix multiplication. And so if I form the vector matrix V, whose elements are V1, V2, Vn, then this is times this coefficient C1, C2, Cn should be all equal to 0. 0, 0, all the way to 0. In other words, sorry, it should be then V times C is a vector and V is a matrix, should be 0. So this is also a vector. V is a vector of dimension, say, how many m by n, C is n by 1, and m is also m by 1, right? So this is the way that we can express the linearly independent vectors. In this case, all these vectors are linearly independent, and then we can say these vectors are spanning the space of this vector space. And also any other vector in this space can be expressed in terms of these linearly independent vectors. So I will shed more light on this by giving you an example. So in Cartesian plane, say this is a Cartesian plane. Cartesian plane, there are two vectors which are linearly independent. So these two vectors are, call them here x, u of x, and u of y. So u of x is 1 and 0, and u of y is 0 and 1. So any other vectors in this space can be expressed in terms of these two linearly independent vectors. So these vectors are linearly independent, and then if you have a vector like 3 and 2, you can always express it in terms of these two linearly independent vectors. So here I can get this is equal 3 u of x. So let's put the notation of arrow in here, plus 2 u of y. Okay, so this is linearly independent vectors, and it has lots of application in linear algebra, in when we deal with the regression model, when we wanted to transform the data into a new space, when you wanted to compress the data, we are looking for linearly independent features collected from a phenomena like in field of science, technology, engineering, health. So next, related to that is rank of a matrix. So rank of a matrix is basically the number of linearly independent columns or rows of that matrix. So if I wanted to define the rank of a matrix is number of linearly independent column or rows of the matrix. So if you have a matrix, let's say matrix A, which has 3, let's say 2, 3, 4 columns, where each of these vectors is a column vectors. Let's say we found that A1, A2, and A4 are linearly independent. Then the rank of A is 3, okay, because 3 vectors. So we know that the always rank of a matrix is minimum of the number of columns or row. That's very important. So always rank of a matrix is smaller than the minimum number of columns or rows. So let's say if A is n by m matrix, then rank of A is always smaller or equal to minimum of n and m. So for instance, if A is equals 3 times 10,000, then rank of A is always smaller or equal than 3. So this is very important to note that, because sometimes if you collect lots of data, but the data has we have small features, then the rank of the linearly independent is equal to number of features of that matrix. So ideally we want our matrix to be full rank. But that means that the number of linearly independent vectors or row or column should be equal to number of row or columns. In this case, we call this matrix a full rank matrix. Otherwise, that means because this matrix is not full rank, then possibly, not possibly, exactly, some of these columns can be expressed in terms of the other columns. So we can conclude these columns are redundant and we can remove them. And finally, I would like to talk about the matrix multiplication. probably you all have so far have multiplied two matrices, and you know how the process is taking place. But in here I just wanted to have a vectorized view of matrix multiplication, and then also provide a simple formula how to compute the matrix multiplication. So let's say if you have A is a matrix belongs to m by n, has m row and n columns, and then B also another matrix with dimensions n by p, then the only way we can multiply b by A is the number of columns of the first matrix is equal to number of rows of the second matrix. So this is extremely important, otherwise we are not able to do the matrix multiplication. So this one should be equal to this one. This is a number of rows, so this is number of columns, and this is number of rows. If you start writing code for some data science problem and you need to do matrix multiplication, one of the common error you get is the matrices are not consistent for multiplication. That means the size is not consistent, meaning that the number of columns of the first matrix is not equal to number of columns of the second matrix. So in this case, if you have here this matrix m by n, this n by p. So always these two numbers should be the same. Otherwise, we cannot do matrix multiplication. Another way, so we can also look at matrix multiplication as in a vectorized form. So if you have A, then I define A as so A1, vector A1, then A2, so A2, then this goes all the way to A. These are number of columns. How many columns? I have n columns, right? Columns, and then B is a matrix has n row. So A1, B1, B2, and then the last column is BP. Then we can do the matrix multiplication by multiplying the row of this matrix by a column of this matrix. So basically what we need to do is to get the first element of each of these vectors and then multiply by the first column, and then get the second row by second column. If you wanted to have a closed formula, this formula looks like this. So we add a page in here. So in general, if I have a matrix A, its dimension is R m times n, another one b whose dimension is r n times p. Then we define the matrix C, A times B, and this matrix belongs to real number of dimension m times p, and then elements of this matrix, let's call them ij. They're equal to sum of k equal to 1 to n I k times b k j. So what does it mean? That means if you have a matrix and you wanted to find the element in the ith row and jth column, then you need to multiply the ith row or the vector in ith row by the vector in jth column. So in other words, if I have A, and A is in vector form is A1 to AI, then all the way to M, and B is a vector of B1 then BJ, BP, then the Cij is basically multiplying AI, this is a vector, the ith row, by BJ, which is also a vector. In other words, I can say Cij is equal to AI vector. This is the dot product of this vector, two vectors. So in order to find the AI element in the matrix multiplication, then we need to do a dot product or an inner product between the ith row of the first matrix and jth column of the second matrix. And then we keep doing for all elements. So this is important to note, this vector form of matrix multiplication, because when we deal with regression models, when we present a matrix form, in there we implicitly do the same thing. That means we are multiplying the row of predictors by the column of coefficients. So also I would like to mention in here, we have different types of matrix multiplication. This is the standard form of the matrix multiplication. We also have the element-wise matrix multiplication. That means we are multiplying element by element. For instance, if I wanted to, for these two matrices, I cannot, so this matrix was m by n. If I wanted to do, and B is n by p, I cannot do the element-wise matrix multiplication, because for element-wise multiplication, two matrices should have the same dimension. But in here, because these matrices are formed in order to be able to multiply them in the standard form of matrix multiplication, but we cannot do element-wise matrix multiplication. Another example, let me just clarify this by an example. Let's say this is a matrix 2, 3, 4, 1, 2, 5, and I have another matrix 3, 4, 1, 7, 8, 2. So I can do the element-wise multiplication for these 2 by 3 matrices. That means I can multiply element by element. The same for the second row, but I cannot do matrix multiplication because the number of columns of the first matrix is not equal to the number of row of the second matrix. They're not equal. In order to be able to do this matrix multiplication, I need to have this matrix 2 by 3, and this one should be 3 by something, another number. So make sure that these two notations are different. In here for element-wise, we use a circle with a dot inside. So this is all components and operations, definitions you need in order to proceed to the next step, in which we use some algorithms and we apply this definition and operations on those algorithms. I have included 2 references in here. There are 2 books. These books are uploaded on Blackboard on book section. So I would encourage you to go and study these books, and also in addition to these slides, I have uploaded the Jupyter Notebook slides where also these topics and these concepts and definition algorithms are given as another extra slides. You can also read those slides. They contain this similar topics and materials, and also some of them are coming with some practical example using NumPy. So far you should be familiar with vectors and matrices, and also by studying the first 2 lectures from the Jupyter Notebook files, you should be able to do to implement these matrix and vectors operations. I have given you a wide range of examples in Jupyter Notebooks files. So I wish you a very good day and night. See you in the next video lectures. Bye.